So this week in Physics 231C, the topic is momentum and related collisions. So that's chapter 6. And chapter 6 has several parts: an introduction to momentum, the law of conservation of momentum, then descriptions of collisions and explosions in one dimension, collisions and explosions in two dimensions, and a related topic, I guess, center of mass. So take notes, and this will be an introduction to chapter 6. So let's start with a summary. So these are the equations that you'll find in chapter 6 that you'll need to understand. First of all, there's the definition of momentum. Momentum is mass multiplied by velocity. It was really Isaac Newton who realized that combination, mass times velocity, is very important in mechanics. You see, you could have a large mass with a small velocity, and that would have a certain momentum. We use the letter P to stand for momentum. P is mass times velocity. That's the definition. Now remember, velocity is a vector. So velocity has a direction. Mass is a scalar. Mass is just a single number. So momentum will be a vector. That's the momentum of, let's say, a large object moving with a small velocity. And what Newton realized is that you could also have a small object with a large velocity. And that could have exactly the same momentum. The masses would be different, the velocities would be different, but the momentum would be the same. And in fact, that combination of mass times velocity is quite important when it comes to interactions between objects. So that's the definition. Now, Newton's second law says that the net force acting on an object is the rate of change of the momentum of that object. We could write it as F equals delta P divided by delta T. That's sort of the wrong way to look at it, actually. A better way to look at it is to say delta P divided by delta T, the rate of change of momentum, is equal to the force, the total force, the combined force, that's acting on the object, whose momentum is P. So you can say F is delta P over delta T, or you could say delta P over delta T is F. In any case, F has to be determined in some other way. The momentum doesn't determine F. The rate of change of momentum is equal to F, but some other theory has to tell you what F is. You know, is F gravity? Or is it just a push or a pull? There are many kinds of forces, and they all have this property that the rate of change of momentum of the object they're acting on is equal to the sum of all the forces, the net force. But mechanics doesn't really tell you what the force is. Mechanics only tells you how it changes the momentum. You have to have some other theory to tell you what the force is. Here's another relation which is often useful. It relates energy and momentum. Remember, we talked about kinetic energy in the last chapter. Kinetic energy, we say kinetic energy is 1/2 mass times velocity squared. Velocity squared. One half mass times velocity squared. Well, velocity is momentum divided by m. Velocity squared will be velocity squared. No. Divided by m squared. So I have m over m squared, that's 1 over m, and I have a 1/2, so p squared over 2m. So kinetic energy, which we already know is important because it's a conserved quantity, well, when combined with potential energy, is determined by momentum. It's the momentum squared divided by the mass. Now, those are the basic equations from chapter 6. A consequence is that two objects with no external forces have constant momentum. The momentum of the first object may be changing. The momentum of the second object may be changing. The sum of the two momenta is not changing as long as there are no external forces. And that's called conservation of momentum. Total momentum is constant in an interaction between objects. Or we can write that in a different way. We can say the change of the first momentum must be equal but opposite to the change of the second momentum. So that the change of P1 plus P2 would be 0. And by Newton's second law, written in this form, the change in the first momentum is the force on the first particle. The change on the second momentum is equal to the force on the second law, on the second particle. And by Newton's third law, those are equal but opposite. So this will be the force on particle 1. This will be the force on particle 2. Well, the force on particle 2 has to be equal but opposite to the force on particle 1. So F1 is minus F2, or delta P1 is minus delta P2. Now that's a conservation law. Total momentum is conserved. And that puts strong restrictions on what can happen in nature. Now that we come to collisions, which is an example of two objects interacting, two objects collide with each other, their momentum will be conserved. There are different kinds of collisions. There are inelastic collisions. And the typical inelastic collision, or the totally inelastic collision, the two particles collide and stick together. So before the collision, you have M1 and V1 initial, M2 and V2 initial. Here's the total momentum. After the collision, both particles are moving together with the same velocity, Vf, because they're stuck together. And so then the momentum is m1 plus m2 Vf. So you see, if you know the masses, this tells you what the final velocity has to be. That's called an inelastic collision. The opposite of an inelastic collision is called an elastic collision. That's where the two particles bounce off each other. So you start out with momentum m1v1i plus m2v2i. The particles collide and bounce off each other, going in different directions maybe. The final momentum is m1v1f plus m2v2f. So you have two particles coming together. They collide. We'll put the final state in a different color. Whoops, I didn't want to put that in a different color. I'll put the final state in a different color. Here's where they collide. They go off in different directions. The total momentum is the same. As the initial momentum. So if this was a head-on collision, the initial momentum would be 0 as the particles were coming together along the east-west direction. And the final momentum would be 0 as the two particles are going apart in the northwest and northeast and southwest directions. That's conservation of momentum. In an elastic collision, another quantity is conserved. It's kinetic energy. So there's a second conservation law. 1/2 m1v1 squared plus 1/2 m2v2i squared, the initial kinetic energy, is equal to 1/2 m1v1f squared plus 1/2 m2v2f squared. That's the final kinetic energy. And those have to be equal. So that's called an elastic collision. And we'll see both examples of both of these things in the LON-CAPA problems. The very last section is called center of mass. If you have a collection of many particles, you can define a special point called the center of mass. The position of the center of mass is the average position weighted by the masses. So it's the total m1r divided by the total mass. It's MIRI summed over all the I values, the total of mass times coordinate, divided by the total mass. So that's the average coordinate weighted by the masses. Okay, so we've had a preview of Chapter 6. Now, before we go on, let's start with a review of Chapters 1 through 5. And in, well, really Chapters 2 through 5, we've defined a number of concepts. And they're all defined by mathematical expressions. For example, there's the position of an object we're watching. That's a vector, r. It has Cartesian coordinates x and y. This would be in 2 dimensions. So the vector r is xi hat plus yj hat. So that's position. It's a vector. Then there's velocity. Velocity is the rate of change of position. So it's delta r over delta t. During a small time delta t, delta r is the change of the position vector. And the ratio, delta r over delta t, is what we call velocity. So velocity is also a vector. And we're using this delta notation. We say, have some quantity q, let's say it's changing in time, Delta Q is Q final minus Q initial. It's the change of Q. It's Q at the later time, t plus delta t, minus Q at the initial time, t. Then we defined acceleration as the rate of change of velocity. Velocity is a vector, so acceleration is also a vector. Then we went to chapter 4, dynamics. Force. Force is also a vector. It's a push or a pull. But, if you push something, you're going to push it in some direction. Or if you pull something, you pull it in some direction. So there's a direction. There's a strength of the force, that's the magnitude, and a direction of the force. So that force depends on which force you're considering. There are many different kinds of forces. And there'll be some theory for expressing that force in terms of things like position and velocity. And Newton's second law says the acceleration of the object, if that's the force acting on it, will be the force divided by the mass. This led then to the definition of work. It's the sum of force times distance over small displacements. F times delta x is the force over one little displacement. If you have a lot of little displacements making up a longer change in position, that will be the total work. It depends on the force. You can define that for any force in the system. It doesn't have to be the net force, but it could be the net force. We define kinetic energy as a half mv squared. That's the energy of motion. It's proportional to the mass. It's proportional to the square of the speed. It doesn't depend on direction. It just depends on the speed. And the kinetic energy work relation, the theorem, says the change of kinetic energy is the net work. The work done by the total force acting on the mass. We define potential energy, also in terms of the force. The change in potential energy is minus F delta x. Force is F delta x. Change in potential energy is minus F delta x. Now, this is especially important if the force changes with position, because if the force changes with position, then the potential energy changes with the position of the object the force is acting on. And what's important about energy is the conservation law. The combination of kinetic energy plus potential energy, we call that the energy, the mechanical energy. That's a constant if the only forces in the problem are conservative forces. I guess I forgot to say here that potential energy doesn't exist for all forces. It only exists for those forces that are called conservative forces. Basically, if a force only depends on the position of a particle, then there's a corresponding potential energy function. Well, that's a review of the first 4 weeks. And now we come to yet another concept of mechanics, momentum. For one-dimensional motion, the momentum is just the mass times the velocity in one dimension. So that's the mass delta x over delta t. You see, momentum can be either positive or negative, just like velocity. If the velocity is positive, then the momentum is positive. That would be one direction on the x-axis. But if the velocity is negative, traveling on the other direction on the x-axis, then the momentum would be also negative. Two-dimensional motion is more complicated because velocity and momentum then are vectors. But it's not really all that complicated because the velocity vector and the momentum vector are in the same direction. They have different magnitudes. In fact, they have different units, but they point in the same direction. Now, for a system of particles, we talk about the total momentum of the whole system. Suppose we have 100 particles. They're all moving around in different ways. Well, then we define capital P as the momentum of the whole system. And it's just the sum of the 100 momenta of the 100 particles. But they have to be added as vectors. So I can use this summation notation where the Greek letter sigma, capital sigma, stands for sum. So this is sum, k equals 1 to n, p sub k. Now p sub k is m sub k times v sub k. Momentum is mass times velocity. Well, if you have a system with 100 particles, you have 100 different masses. So there's no, well, you could add all the masses. But these can be all in different directions. So anyway, you have to calculate the momentum for each particle separately. That's its mass times its velocity. For the kth particle, that's m sub k times v sub k. And v is the rate of change of velocity, so it's delta xk delta t, delta xk divided by delta t, times I hat, so that's the velocity component in the x direction, plus delta vy, plus delta x, plus delta yk for particle k. Its coordinate is y sub k. The change in yk divided by time is the component of velocity in the y direction. The unit vector is j hat. So that defines a certain concept called momentum. And now we're going to see why is that interesting and important. Okay, so we've defined momentum of a particle. P is mass times velocity. And now we're going to write down various relations that involve the momentum of a particle. So the first relation is the rate of change with respect to time. Delta P over delta T. There's some force acting on the particle. There may be many forces acting on the particle. We combine those into the net force. So the net force is the vector sum of all the forces. The rate of change of momentum is equal to the net force. Delta P divided by delta T is the net force. And we use this delta notation where delta is not a quantity, delta is not a number, delta is an operation. It acts on some quantity which changes. And delta Q, some quantity Q, is the change of Q. And of course, delta T is the change of time. So that's a little time interval. Now, suppose you're timing something with a stopwatch. Suppose you start the stopwatch at 0 and you stop it at 1 second, then delta T is 1 second. It's that time interval. Now this is a theorem, so let's prove it. Delta P is P at T plus delta T minus P at T. Final value minus the initial value for that time interval. P is mv, so I have mv at T plus delta T minus mv at T. Now, assuming that the mass is not changing, so we're just dealing with a particle moving around, then I have a constant factor here of m. So I can factor out m. I have m times v of t plus delta t minus v of t. That's delta V. So this is m times delta V if we're talking about the motion of a particle. This might fail, for example, in the case of a rocket, where the mass is changing. As the rocket is firing, it's expelling hot gases out the back of the rocket. But for particles, delta P is mass times delta V. Delta V is acceleration times time. In the time interval delta T, the acceleration multiplied by that time is the change in velocity. Acceleration is rate of change of velocity. Now I can group mass times acceleration. That's the net force. That's Newton's second law. So I have F net delta T. If I divide both sides of the equation by delta T, I get this relation. So you see, this is actually just a different way of writing Newton's second law. Newton's second law says ma is F. Well, for a particle, ma is the rate of change of P, momentum. In fact, in Newton's book, in which he first wrote down the laws of motion, this is the form that he used for what we today call Newton's second law. Newton said the rate of change of momentum, I don't think he used the word momentum. I don't know who invented the word momentum. It wasn't Newton, but it was Newton who invented the concept of mass times velocity. Somebody invented the word momentum, so what we say now is the rate of change of momentum is the net force. And Newton wrote the equivalent of that in his book. Of course, his book was written in Latin, so can't exactly write down exactly what he said. Another relation is kinetic energy is P squared over 2m. Well, I talked about that a minute ago. Kinetic energy is a half mv squared. That's a half mp over m squared. That's P squared over 2m. So that's a relation between kinetic energy and momentum. In Newton's time, Newton believed momentum was really the important quantity, mass times velocity, because of this law of motion. There were other scientists at that time who believed that more relevant was mass times velocity squared, or mass times speed squared, which Newton didn't really talk about. Of course, today we know they're both important. They're both kind of equally important in different ways. Everybody knows that energy is important. Now, why is momentum important? Well, that's the next part of this chapter. Momentum is important because the total momentum of an isolated system is conserved. Conserved means constant, constant of the motion, constant in time. As the system changes, the momentum does not change. So this is one of several important conservation laws in physics. A conservation law states that some quantity is constant in time as the system changes. So it's not that the system is static. The system is evolving. But there's some quantity which is not changing. That's called a conservation law. And there are a number of conservation laws that are, essential laws of nature. The conservation law places a strict restriction on the changes that can occur in a system. Now, we already saw an example of this back in Chapter 5, conservation of mechanical energy. If you have a particle moving under the influence of a conservative force, let's say the net force is just called F, and F can be written in terms of a potential as minus delta U over delta X I hat minus delta U over delta Y J hat. So F in some direction is the rate of change of potential energy. Actually, the rate of decrease of potential energy because of the minus sign. Now, by the work energy theorem, delta K is the net work. That is to say, it's the work done by F. It's the sum Fx delta X plus Fy delta Y. Work is force times distance, or force times displacement, I really should say. So work is force times the displacement. If there's displacements in 2 dimensions, then you have the component of the force in the x direction times delta x plus the component of the force in the y direction times delta y. And that gives you the net force. Now, Fx is minus delta u over delta x. Multiply that by delta x. Then I have Fy is minus delta u over delta y. Multiply that by delta y. See, the delta x cancels the delta x. Delta y cancels the delta y. I just have here the sum of minus delta u in all the x displacements plus all the y displacements. So that's just minus delta u. Here I'm using the little delta notation, which stands for a small kind of infinitesimal displacement. Here I'm using the capital delta displacement, the total displacement. So the total change in kinetic energy is the negative of the total change of potential energy, or delta K plus delta U is 0. Or equivalently, K plus U is constant. Kinetic energy may be increasing. If so, potential energy is decreasing by the same amount. Or potential energy might be increasing. In that case, kinetic energy is decreasing by the same amount. So K plus U is constant. That's what we call the mechanical energy, K plus U. Now, of course, all this is based on the assumption that the only force acting is a conservative force. When they're non-conservative forces, then things are a little different. There can be energy transfers, for example, by heat. So, for example, friction is not a conservative force. Mechanical energy is not conserved when friction is acting. Total energy is conserved. Thermal energy is transferred in the form of heat. Well, okay, so this conservation law, conservation of energy, can be used to solve certain mechanics problems. You can say E initial is equal to E final. So m over 2 v initial squared plus u of the initial position must be the same as m over 2 times v final squared plus u of the final position. So I can make some conclusions about final speed, for example, without doing the whole calculation of acceleration. I don't have to follow the entire acceleration and force relations in order to figure out the final speed, because I just have this equation for final speed. So, conservation of energy makes certain calculations very easy. And now we have another conservation law, conservation of momentum. All right, so now we're going to see how the conservation of momentum applies to problems such as collisions. So we'll consider an isolated system. What's meant by an isolated system is there are two particles interacting with each other, exerting forces on each other, but no other forces involved. So there are no external forces. The system consists of two particles, and nothing outside of those two particles is playing a role in the motion. Now, as the particles move, they obey Newton's second law, which we can write in terms of momentum. We can say the change in momentum of the first particle is the force times the change in time. So during a small time interval delta t, the force acts on particle 1. It's exerted by particle 2, so we'll call that F sub 2, 1. Now, in the same way, for the other particle, particle 2, delta P is F acting on particle 2, delta T. So F sub 1, 2 means the particle exerted by, the force exerted by particle 1 acting on particle 2. And that produces a change in the momentum of particle 2, which is equal to the force times the time interval. Now, by Newton's third law of motion, the law of action and reaction, F21 is minus F12. That is to say, the forces are equal but opposite. So particle 2 exerts a force F21 on particle 1. At the same time, particle 1 exerts a force F12 on particle 2, and those are the action and reaction. Which one is the action and which one is the reaction is kind of arbitrary. That's just a matter of what you want to call action and reaction. F21 is the reaction to F12, and F12 is the reaction to F21. So you consider either one to be the action, and then the other force would be the reaction. Now add delta P1 and delta P2. It's F21 delta T plus F12 delta T, but F21 is minus F12. So that's minus F12 plus F12. That's 0. So delta P1 plus delta P2 is 0. In other words, P1 plus P2 is constant. If the momentum of particle 1 changes, the momentum of particle 2 must change by the same amount, but in the opposite direction. And so that means the total momentum of this two-particle system is constant, where what I mean by total momentum is the sum of the momenta of the two members of the system. Now, for a system with n particles, by exactly the same reasoning, the sum k equals 1 to n p sub k is constant. And we would call that the total momentum of a system of n particles. So that's conservation of total momentum. Particle 1, its momentum may change. Particle 2, its momentum may change. But the sum of the two momenta does not change. Now, of course, these are vectors, so they have to be added as vectors. It's the vector sum, which is constant. And let's work out an example, a simple application, a one-dimensional collision. So we have, moving along some line x, some object with mass m1, some other object with mass m2. And we'll call v1 the velocity of m1, and we'll call v2 the velocity of m2. Now v1 and v2 could be vectors in opposite directions, or they could be vectors in the same direction. Now, for a perfectly inelastic collision, the total momentum is conserved. So capital P initial, that's P1 plus P2 before they collide, must be the same as capital P final, P1 plus P2 after they collide. That's called an inelastic collision. Well, that's momentum conservation for any kind of collision. But in particular, an inelastic collision means that when the two objects collide, they stick together. So after the collision, you just have one object with the mass m1 plus m2 moving in some direction with some velocity vf. So we have two equations. This equation for momentum conservation, and then we can solve that equation for the final velocity. Just divide both sides of the equation by m1 plus m2. The final velocity of the pair of particles will be m1 v1 plus m2 v2, divided by m1 plus m2. This is the initial momentum, the sum of the two momenta, and the final momentum is the combined mass times the final velocity, since they're both moving together, stuck together. So divide both sides of the equation by the total mass, you get the velocity of the two particles stuck together. Now, this is only one-dimensional. In other words, this is like a head-on collision. What will be more interesting is when you have two-dimensional collisions where the directions of the particles will change. Now let's work out a special case. Let's suppose V2 is 0. So this object is at rest before the collision. So it's sitting there minding its own business. This particle comes in and hits it. And let's suppose that M2 is 3 times M1. So you have a mass, I don't know, maybe 1 kilogram. And here's a mass of 1/3 of a kilogram, which comes in and hits it. Then they stick together. You know, depends on what they're made of. So suppose they're made of some material which is very sticky or something. So when they hit each other, they stick together. Or suppose they have bumpers and the bumpers get locked after they collide. Well, then they'll both move off to the right. You have particle 1 coming in, going to hit particle 2. So that's the initial state. And then afterwards, you have particle 1 and particle 2 sticking together, going off in some velocity, Vf. So here was V1. V2 was 0. And what is Vf? Well, it's m1 plus m2. Now m2 is 3 times m1. So it's 4m1 times v1 divided by 4. No, divided by 4m1. But the m1 in the numerator cancels the m1 in the denominator. So you have m1 times v1 plus 0, because v2 is 0 before the collision, divided by m1 plus m2. That's 4m1. So this velocity, as the particle moves away, it's moving with 1/4 the initial speed. So, if this comes in at 10 meters per second, they stick together, they move away at 2.5 meters per second. And that's because the ratio of the masses is 1 to 3. We're assuming that m2 is larger than m1, 3 times m1. So when they stick together, they'll end up moving sort of slowly. If m1 were larger than m2, then when they stick together, they'll go off with pretty much the same velocity as the first particle. It'd slow down a little bit because of the second particle, but to a first approximation, the velocity after the collision would just be, again, v1. It'll be a little bit less than v1. Now, the kinetic energy is not conserved. In other words, this initial state has some energy. It has energy 1/2 m1 v1 squared. And no kinetic energy for the second particle, it's at rest. This final state has some energy, but it's smaller than the initial energy. So in other words, in colliding and sticking together, the particles lost energy. Let's calculate the change in energy. The only energy involved here is kinetic energy. So what's delta K? Well, it's the final K, 1/2 the mass times the velocity squared. So that's 1/2 m1 plus m2 times v final squared, minus 1/2 m1 v1 squared minus 1/2 m2 v2 squared. The kinetic energies of the two particles before they collide. But v2 is 0. And vf is m1 v1 divided by m1 plus m2. So if you work out the algebra for this expression and simplify it, it'll be negative. It'll be negative, so the kinetic energy has decreased. So somehow the system lost energy, or at least it lost kinetic energy. Now, this expression is incorrect. I don't know how I got that answer. That's not correct, but I'll let you work out the correct answer for the change in kinetic energy. At least for this problem, where v2 is 0, I just have 1/2 m1 plus m2 m1 squared over m1 plus m2 squared, v1 squared, minus 1/2 plus 1/2 minus 1 half m1 v1 squared minus 0. So it's a step of algebra to simplify this. And you'll find that it's negative. So in an inelastic collision, where two particles stick together, mechanical energy is reduced. Kinetic energy in this case. There's no potential energy here. However, it's a universal principle of science that total energy is constant. So some other form of energy must have increased by the same amount that the kinetic energy decreased. So where did that energy go? Well, for example, whatever is causing these to stick together has done some kind of, suppose these two are two pieces of metal and they crunch each other together and they're crushed. Well, they've lost energy from the potential energy of their dimensions. So in an inelastic collision, kinetic energy is converted into some other form of energy. But momentum is conserved. Well, let's work out another application now, a two-dimensional elastic collision. So when I say elastic, I mean the kinetic energy is conserved. So unlike an inelastic collision where the two objects kind of crumple each other up and get crashed together and, change their shape so that they stick together, in an inelastic collision, they just bounce off each other. And they come out with the same shape that they went in with. Now, also, let's consider a two-dimensional case where it's not a head-on collision. We could do a head-on collision, but just to be more general, let's consider a two-dimensional collision. So here's particle 2, mass m2, and let's suppose it's initially at rest. And here's particle 1, and it's initially coming in towards the collision with a velocity v1. Then they collide. Particle 1 goes off at some angle theta, and this is called the scattering angle. So that angle is called theta. Particle 2 has to recoil because they don't stick together. It'll go off in some direction, and that's another angle. So we'll call that angle phi. Kind of a recoil angle. And each particle will have a speed. Let's call v1f the speed of the outgoing particle 1, and v2f the speed of the outgoing particle 2. And now write down the equations that'll describe the collision. Well, for any collision, momentum is conserved. So we can say the initial momentum is the same as the final momentum. Now, momentum's a vector. So we have to divide the momentum into the x component and the y component. So we'll have an x component of momentum px and a y component of momentum, py. Now, initially, py is 0 because nothing is moving in the y direction. Momentum is mass times velocity. Well, the velocity is only in the x direction, and it's owned by particle 1. So, initially, py will be 0 before the collision. And it'll also be 0 after the collision because it's conserved. So here's py. It starts out at 0. It ends up at m1 v1 final sine theta minus m2 v2 final sine phi. And that also has to be 0. Because P initial is the same as P final. Now that's the y component. What about the x component? Well, initially, all the momentum belongs to mass m1. So the momentum before the collision is just m1 v1. But then after the collision, both particles will have some x component of momentum. It'll be m1 v1 final cosine theta. That's the projection onto the x-axis for v1, plus m2 v2 final cosine phi. That's the projection onto the x-axis for the momentum of mass m2. So there are two equations relating these various variables. But there's one more equation. For an elastic collision, energy is conserved. That is to say, kinetic energy. So the initial kinetic energy is 1/2 m1 v1 squared. It's the kinetic energy of the incoming particle. And the final kinetic energy is 1/2 m1 v1 final squared. That's m1's kinetic energy, plus 1/2 m2 v2 final squared. So you have three conservation laws, px, py, and k. Now, of course, k is a scalar. P is a vector, so it has x and y components. All right, here we have three equations, but four unknowns. Suppose I take the masses as known, and the incident particle, its speed is known. Then the unknowns are v1 final, v2 final, theta, and phi. So these two angles, v1 final and v2 final, those are unknown. I have more unknowns than I have equations, but that's because theta is not determined by these conservation laws alone. To determine theta, you have to have more information. For example, I've drawn this little sphere M1 as slightly displaced from the x-axis so that it doesn't hit M2 head on. It hits it a little bit displaced from the center. That causes M1 to go off at an angle theta. It's scattering. And then M2 has to go off at its angle phi to conserve momentum in the y direction. Well, I didn't tell you exactly how much this was displaced from the x-axis, so I didn't tell you enough information to determine theta. But let's say we're just observing this collision, and let's suppose we observe theta, we measure theta, the scattering angle. Well, then we have three equations with three unknowns. So if in addition to the initial state I tell you the scattering angle, then the three equations, the three conservation laws, will determine all the other unknowns, namely V1 final, V2 final, and phi. So if we're given the masses and V1 and the scattering angle, then the three equations will determine the three unknowns, phi, V1 final, V2 final. And I won't go any further with this in the video. There are obviously many special cases. You might have a head-on collision where theta was equal to 0. And phi would also turn out to be 0, so that the y component of momentum is conserved. Maybe M1 is lighter than M2. So M1 comes in and hits M2 and bounces back. So then theta would actually be 180 degrees. And phi would be 0 degrees. But on the other hand, if M1 were heavier than M2, then when they collide, M2 will go off at a higher velocity. M1 will continue moving to the right, so the scattering angle in that case would be 0. But there would be a change in the speeds. So there are many special cases. This is too general to try to solve this in complete generality. I'll just say, read the examples in chapter 6. You'll see some special cases. One interesting case is billiards or pool. A pool player knows that when the cue ball hits the 8 ball, the cue ball goes off in one direction, the 8 ball goes off in the other direction, and the angle between the two vectors, the two final vectors, is 90 degrees. So a skilled pool player can predict exactly where the cue ball is going to go and where the 8 ball is going to go. And it turns out, because the two masses are equal, this will be a 90 degrees. That's not always a 90 degrees. It's a 90 degrees if M1 is equal to M2. So there are many special cases like that, and I'll just leave it to you to find the examples in chapter 6. Now there's one final section of chapter 6 which defines the center of mass of a system of particles. Suppose you have a system of particles like this. Suppose you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose you had 10 particles. And I've drawn it as if they were all the same, but they could all be different. You know, they could be different colors, they could be different sizes, they could have different masses. Some might be heavier than others. You just have a system, an isolated system with 10 objects. And, you know, suppose this is moving. Suppose this whole thing is moving off in some direction. And they might be colliding with each other. Or if these were asteroids or planets, these could be exerting forces on each other, forces of gravity. So there can be interactions between the different particles in the system, but there's no external force. It's just this isolated system. Well, the total momentum of that system will be constant. As they move around. Even if the individual elements move around in different relative positions, the total momentum will be constant. Now, the center of mass is a special point in the space which is equal to the average position of the particles weighted by their masses. So in other words, the vector position of the center of mass, r sub center of mass, is the average of the positions of the 10 particles weighted by the masses. So it's the sum mr for k equals 1 to 10 divided by the total mass, the sum m for k equals 1 to n. If all the masses are equal, that's just the geometrical mean position. But if the masses differ, then this gives heavier weight to the higher masses, less weight to the lower masses, and so you get some kind of average position, which is weighted by the masses. So this might be the center of mass point. It doesn't have to be one of the points of the particles in the system. It could be someplace, someplace separate from any of the particles. That's the center of mass point. Now, the center of mass is related to the total momentum in an interesting way. The total momentum of the system is, call it P, is the total mass times the velocity of the center of mass. So if you think of these as exerting forces on each other, as this system of 10 particles moves off in some direction, the relative positions are changing. But the center of mass point is just moving with a constant velocity. V sub cm is the velocity of the center of mass. And that's a constant because P is a constant. So, if you have a group of particles that are moving around, in a certain sense, you can combine them into one grand particle whose position is the center of mass and whose mass is the sum of the masses of all the individual parts. So we've been doing a lot of problems where we assume there's a particle. Well, it doesn't have to be a single particle. It can be a whole bunch of particles. And, you could imagine something shaped like a peanut, which we subdivide into many small parts, and each part is a little particle. The whole system consists of all the parts. Someplace there's a center of mass point. We have the total mass, and the total momentum of the peanut is just the total mass times the velocity of the center of mass. So center of mass is a concept, it's a kind of geometrical concept, which is useful when you have a system with many parts. And there'll probably be some Lon Kappa problems where you have to calculate the center of mass of some object. Suppose you have a sphere. Where's the center of mass? Well, if the mass density is uniform, then the center of mass is just at the center of the sphere. So when we come to talk about the motion of planets, when we say we're following the motion of a planet, what we really mean is we're following the motion of its center of mass point. All right, so that completes the introduction to Chapter 6. Now you should read Chapter 6. You've had an introduction to the topic. And then start doing the homework problems on the Lon Kappa assignment, which is due next week. And about half of the problems in that assignment came from momentum.